Okay, so in this video we want to continue to look at the binomial probability distribution, but we're going to look at the inbuilt functions available to us in the CAS to enable us to solve more complicated problems. At the end of the last video, I linked to a video by Brady Harron from Numberphile, where he was looking at trying to roll a one-roll Yahtzee, so by rolling 5 dice, getting all dice the same, and he was calculating and talking about some probabilities around that, and we calculated and confirmed some of his probabilities. I'll link also to another follow-on video from that, just out of interest if you would like to watch. It became a thing that his followers really jumped on, and they sent him lots and lots of videos of them rolling one-roll Yahtzees, and there's some amusing instances of how people did it, or how they or just their celebrations when they finally got there and how long it took them to do it. So I'll link to that just out of interest if you're keen to have a look. Another video that followed on from his original one-roll Yahtzee video was by another maths YouTuber called Vi Hart, and Vi also decided to get involved, but she mixed things up a little bit. So she attempted to get a one-roll Yahtzee by rolling 6 tetrahedral dice. So Brady rolled 5 regular die, so 5 die that each have 6 sides. She is rolling 6 die that each have 4 sides. Okay, so she wanted to she calculated some probabilities here, and she also recorded herself attempting to roll a one-roll Yahtzee using these die. So we want to know, first of all, what's the probability of obtaining a one-roll Yahtzee using these dice? So again, the same logic we used at the end of the previous video. In her first roll, it doesn't matter what she rolls, so probability of 1. Okay. The second roll has to match the first roll. So there's 4 sides to this die, so whatever she rolled in the first roll, there's 1 on 4 chance that not the first roll, sorry, whatever number the first dice displays, there's a 1 on 4 chance the second die displays the same number. And again, 1 on 4 probability that the third die will display the same number, 1 on 4, and she's got 6 of them, so 1 on 4, 1 on 4. So it's essentially 1 on 4 to the power of 5. Okay, so that will be 1/4 to the power of 5. So that is 1 on 1024. Now, if you've watched the video, which I'll have linked previously, she gets the Yahtzee after only 382 rolls. So we want to think about, well, what would be the probability of that actually happening? That's a lot less than what we might expect, given it's only a 1 in 1024 chance. So what is the probability that she would actually get the Yahtzee in 382 rolls? So again, if we set this up, if x is the number of Yahtzees, x is a binomial variable, we're going to do 382 rolls in this instance. Probability of getting a Yahtzee at each roll is 1 in 1024, and we want to know what's the probability that she gets at least 1 in the 382 rolls, which is 1 minus the probability that she gets no Yahtzees in the 382 rolls. So that is 1 minus 382, choose 0, 1 on 1024 to the power of 0 times 1023 on 1024 to the power of 382. So again, this is 1, this is 1, so it's just 1 minus 1023 over 1024 to the power of 382. So if we work that out, 1 minus 1023 divided by 1024 to the power of 382 as a decimal is about 0.31. So it's approximately 31% chance of her actually doing that with these dice. So she got quite lucky in her video. Okay, let's continue to look at our probability distribution. Let's start with a really simple example. Fair die is rolled 50 times. Okay, so we've got x is, in all the questions we're interested in the number of 6s. Okay, so x is the number of 6s observed. X is distributed binomially. We're rolling the die 50 times, so n is 50, and p, it's probability of rolling a 6 with a fair die, so it's 1 on 6. Okay, what is the probability, correct to 4 decimal places, of obtaining no 6s? Okay, so that is the probability that x is equal to 0, so the number of 6s is 0, and that is going to be 50 choose 0, 1/6 to the power of 0, 5/6 to the power of 50. So that's just 5/6 to the power of 60, sorry, to the power of 50. Correct to 4 decimal places is 0.0001. So very low chance of getting no 6s when you roll the die 50 times. What is the probability, correct to 4 decimal places, of obtaining at least 1 6? Okay, so probability that x is bigger than or equal to 1 is the same as 1 minus the probability that x is 0. And so it is 1 minus my previously calculated answer, which is 0.9999 to 4 decimal places. What is the probability, correct to 4 decimal places, of obtaining at least 20 6s? So probability that x equals 20. Sorry, not equals 20, at least 20. X is bigger than or equal to 20. Okay, so that would be probability that x equals 20 plus the probability that x equals 21 plus all the way up to the probability that x equals 50. And even if you tried to make it a bit more efficient, it would be 1 minus the probability that x equals 0 minus the probability that x equals 1 all the way up to probability that x equals 19. Okay, either way, it's going to be a lot of work. Okay, and imagine now if we're going to do 100 trials. So we've looked at, in the previous video, some very select examples where we can use our formula nice and easily to calculate probabilities. However, it gets out of hand pretty quickly. And so we don't want to only rely on the formula, although I must say you do need to know the formula and you do need to know how to execute it. So by the formula, I'm referring to n choose x, p to the power of x, 1 minus p to the power of n minus x. Okay, you absolutely need to know that, which is why I introduce it separately before I show you how you can do it with the CAS. So in this situation, we would use these inbuilt binomial distribution functions involving our CAS, okay, or in our CAS. So if you press menu, 5 for probability, 5 for distributions, the binomial ones are down towards the end of this list. Oh, sorry, scroll down here. So A and B and C and D are also relevant. We'll come to those in the next video. So A and B are probably what we're looking at here. We've got a choice between binomial PDF, PDF stands for probability density function, or binomial CDF, which is the cumulative density function. So you would choose PDF if you want to calculate the probability that x is equal to a particular value. You would use CDF, the cumulative function, if you want to calculate the probability that x is bigger than or equal to something, or less than or equal to something, or between two values where you're going to need to add up a number of separate probabilities. Okay, so if we want to have a look at this example we've just looked at here, we would use CDF because we want to look at a cumulative probability from 20, 21, 22, 23, 24, all the way up to 50. Okay, so we would choose option B, so it would be menu 55B. And then we need to give it the number of trials. Now in this problem, I'm looking at this example here, okay, we had 50 trials. We need to give it the probability of success. We were rolling a fair die and interested in the number of 6s, so probability of success was 1/6. And then we need the lower bound. So when x has to be bigger than or equal to 20, the lowest x value we want to calculate the probability for is 20. And the upper bound, we've only got 50 trials, so we can only have at most 50 successes. And then we press enter, and we get our answer. Okay, so we can't even write that accurate to 4 decimal places. Yes, we can. It would still be 0.0001, but it's smaller than our answer that we had previously. Okay, so we're going to have a look at some examples of how we do that. So this box here in your notes talks through the difference between PDF and CDF. So a particular x equals a particular value, you would use PDF, and you have to enter in n, p, and the x value you want to calculate the probability at. CDF, you're going to calculate the probability for a range of x values, so you have to enter n, p, and the lower and upper bounds for those x values. And there's a series of examples that it talks through here, but I'll leave you to have a look at those. We might just get on with the examples. Actually, one thing I will highlight before we move on from here is, obviously if x is less than or equal to 25, when you've got 50 tosses of a coin, okay, then that's the second row here. Sorry, no, it's the third row here. Then the lower bound in that case would be 0. The smallest number of successes you could have would be 0 successes up to and including 25 successes. If x has to be bigger than 10, the lower bound isn't 10. 10 successes isn't in that range of values. X has to be bigger than 10, which means it has to be bigger than or equal to 11. It has to have at least 11 successes. So the lower bound would be 11 up to the upper bound, which would be 50. If you want x between 20, including 20 but not including 30, the lower bound would be 20, but the upper bound would only be 29. Okay, so you need to be a bit careful about your inequalities and precise about them, because they're going to make a difference if you enter in the wrong lower bound and upper bounds. Right, let's just work through some examples. Records show that a certain medication will successfully cure a particular disease in 1/4 of the cases treated. If 7 patients are given medication, what is the probability, correct to 4 decimal places, that 2 will be cured, at least 2 will be cured? Okay, so we first of all need to define our variable, x, y, z, p, whatever. No, don't use p, probabilities can get a bit confusing. Okay, so I might go with c is the number of cured patients. Okay, c is a binomial variable. The patient is either cured or not cured. The probability of them being cured is 1/4 every time, doesn't change. Obviously, again, a very simplified example of the real world, but for all intents and purposes here, we're going to treat this as a binomial distribution. So we need n. 7 patients were given the medication, so n is 7. And we need p, which is the probability of success, so the probability that a patient is cured, and we know it will successfully cure a particular disease in 1/4 of patients. Okay, so there's our setup. And then we want to know the probability that 2 will be cured. So probability that c is equal to 2. Now we can use the formula for this. 7 choose 2 times 1/4 to the power of 2 times 3/4 to the power of 5. Fine. But let's practice being able to use our CAS. So menu 5, 5. And in this case we want binomial PDF, because we're just calculating the probability at one particular x value, or c value in this case. So number of trials is 7, probability of success is 1/4, and the x value is 2. And we want correct to 4 decimal places. It tells us that in the question. And when we do that, we get 0.3115, correct to 4 decimal places. I just want to be clear about that. You can actually, even if you've got just the 1x value, you can, if you choose, always use menu 55b, the cumulative density function. And when you do that, so n is still 7, probability of success is still 1/4, or you could type 0.25, you would just simply type the lower bound and upper bound as both being 2. So if you want, you could always use menu 55b, regardless of whether it's a cumulative distribution or just one particular value. Part B, the probability that at least 2 will be cured. So C is bigger than or equal to 2. Okay, so this time menu 55, definitely B. We want a cumulative distribution, because we're calculating 2, 3, 4, 5, 6, 7 cured patients. So N is 7. Probability of success is 1/4 or 0.25. Lower bound in this case is 2. We want at least 2, so 2 is the smallest number of cured patients. Up to, there are only 7 patients being given the medication, so the upper bound is 7. And 4 decimal places is 0.5551. Alright, example 2. A survey of the population in a particular city found that 40% of people regularly participate in sport. What is the probability, correct to 4 decimal places, that fewer than half of a random sample of 10 people regularly participate in sport? Okay, so let's have S is the number of people participating in sport, or regularly participating in sport. And S is a binomial distribution. Someone either participates or they don't. The probability of this population participating is 40%, etc., etc. Okay, so N, we need N, the number of trials, or the number of people that we're looking at. So we're looking at a sample of 10 people, so N is 10, and the probability that any one of those people participates in sport is 0.4. we want the probability that fewer than half of a random sample of 10, so fewer than 5, probability that S is less than 5. Okay, so we need to be a bit careful here when we put in our upper bound, because 5 is not the upper bound. Less than 5 means the most that can be participating in sport is 4. Okay, so I'm going to use menu 55B. Number of trials is 10. Probability of success, probability someone does participate is 0.4. My lower bound in this case will be 0 up to 4. So we want to look at the probability that either none, 1, 2, 3 or 4 of the sample of 10 participate in sport. And we want, again, correct to 4 decimal places, 0.6331. Okay, example 3. A multiple choice test has 10 questions, each with 4 possible answers, only one of which is correct. Find the probability that a student who guesses the answers to every question, so randomly chooses an option at each choice, will have no correct answers, etc. Okay, so let's have a look at, let's make A equal to the number of correct answers. You can choose whatever letter you want. Correct answers. Okay, A is a binomial distribution. Okay. There are only 2 possibilities. They either get the answer or correct or they don't. That's the 2 options at each choice. N is there are 10 questions in the test, and the probability of them answering each question correct, given that they guess every answer, so they're randomly selecting a choice, the probability therefore, if there's 4 possible answers and only 1 is correct, the probability their randomly guessed answer will be correct is 1 in 4, 1/4. Part A, we want the probability that they get no correct answers. So probability that A, the number of correct answers, is 0. So menu 55, now I use A. It's a PDF, just the one value. N is 10, P is 1/4 or 0.25, and the X value is 0. And enter. We want correct to 4 decimal places. There is a only 0.0563 probability that in the 10 question test they will answer none of them correct. So that's good news. Okay, then we want part B, the probability that 6 or more answers are correct. Give your answer correct to 4 decimal places. So probability that 6 or more answers are correct, that is the probability that A is bigger than or equal to 6. The number of correct answers is bigger than or equal to 6. Menu 55B. Number of trials is 10. Probability of success is 1/4. Probability, lower bound is 6 and upper bound is 10. So 0.0197, correct to 4 decimal places. Part C, the probability that every question is correct, given that they have 6 or more correct. So probability that A is equal to 10. The number of correct answers is 10, given that they have at least 6 answers correct. Okay, so we need the intersection of those 2 things. Probability that A is both equal to 10 and bigger than or equal to 6 over the probability that A is bigger than or equal to 6. So intersection, if the number of answers correct has to be both 10 and bigger than or equal to 6, the only intersection, the only outcome in common between those 2 sets is, sorry, not X, A has to be equal to 10 over the probability that A has to be bigger than or equal to 6. So we've already got the denominator from the previous question, 0.0197. Probability that A is equal to 10, menu 55A, 10 and 1/4, and we want 10. This should be a very low probability, I think. Alright, so yes, 0.000, how many zeros have I got there? 1, 2, 3, 4, 5, 6 zeros, 9537 over 0.197. Okay, so it's going to be that answer there. Now that's not our final answer, so don't worry about the rounding of that. Divided by that answer up there. And we want this answer correct to 6 decimal places. And you'll see, I said normally they'll ask you for 4. There'll be reasons why they change that. They need to ask for 6 here because to 4 decimal places this would essentially not exist. It would be 0. So to 6 decimal places, 0.000048. So a very low probability of getting all correct, given that they have 6 correct, and even lower probability of having all of them correct without the condition. Okay, very small part of the course. I've never seen it assessed, but it is still in the course. The graph of the binomial distribution is essentially constructing the probability distribution, so working out the probability for each possible value of the variable, and then just plotting those values. So we've got a binomial random variable with n equals 5, so we've got 5 possible trials and the probability of success is 2. So in 5 trials we could have either 0, 1, 2, 3, 4 or 5 successes. We can calculate each of those binomial probabilities. So for example, this probability here is coming from menu 55A, number of trials is 5, probability of success is 0.2 and the x value is 0, and we get 0.3277 to 4 decimal places. We can edit that and change it to 1 to work out the probability when x equals 1. It is 0.4096, correct to 4 decimal places. Okay. The other thing you can do with your CAS is you can actually generate all of those numbers at the same time. If you do menu 55A, so binomial PDF, and you put in n and p, but you leave the x value blank, it says optional, it will then give you all the probabilities listed as a set. So the first number there is the probability that x equals 0, second number is x equals 1, third number is x equals 2, x equals 3, etc. So you can get all the probabilities straight away. And then the graph is simply plotting that. Okay, and we normally draw a straight line it's technically only a series of points. So it's the point 0, 0.3277, which is this point here, the point 1, 0.4. So it's essentially only a series of points, but just to make it so that we can sort of see what's happening a bit clearer. We certainly don't join the points because it's a discrete random variable. It's not possible for x to be anything between 0 or 1. So that the points don't get lost on the axes, we just draw these vertical lines in, so you're sort of getting almost a bar chart effect where you can see what's happening. I've already talked about how to generate the complete PDF using the CAS. Looking at the graph of a distribution allows us to observe the shape of that distribution. Okay, and what we will see is if the probability of success is 0.5, we'll get a nice symmetric distribution. The peak will be in the middle and everything will be nice and symmetrically distributed around that. If our probability is less than 0.5, we will have a positively skewed distribution. Now, positive skew is when, and it always seems very the opposite of, it's unintuitive to me to describe this as positive skew. And I'm sure there'll be statisticians who will be thinking, what do you mean it's unintuitive? It makes perfect sense to me. But to me, you've got most of the distribution at the lower end. It doesn't strike me as being positive. It strikes me as being a bit more negative. I had it described to me once. You can think of it as the data has been pushed from the positive side, okay, and we've created this positive skew. We get negative skew when the data is pushed from the negative side and it's peaking mostly over to the right. Okay, positive skew when it's mostly over to the left, symmetric when it's in the middle. Okay, so probability bigger than 0.5 will get negative skew, probability equal to 0.5 will get a symmetric distribution, probability less than 0.5 will get a negatively skewed distribution. I've never seen skewness assessed in methods either, but again it does remain in the course, being able to describe your distribution. The other thing to note is the peak of your distribution should be around the expected value. Okay, so 20 times 0.5, 10 is my peak here. 20 times 0.2, okay, would be 4. My peak is happening at 4. 20 times 0.8 would be at 16. My peak is happening at 16. That is the expected thing that would happen. And in the case of a binomial distribution, it's also technically the most likely thing to happen. Okay, let's just finish with one final example, generating our own probability distribution and graph. A game of chance is played in which the probability of winning is 1/3 and the game is played 5 times. So let's first of all fill in the PDF. So I'm going to go with menu 55A and I'm going to leave my X value blank. My number of trials here is 5. My probability of success is 1/3. I'm going to leave the X values blank and I'm going to get all my probabilities. I'm just going to put them each to 4 decimal places in here. So this is 0.1317. This is 0.3292. This is also 0.3292. Sorry, I think I've gone past here. I'll go from the other end and then I'll go back to the middle. 0.0041. 0.04. There's so many digits there. 412. Correct to 4 decimal places. and just going to need to scroll along manually to get that one in the middle that I just couldn't quite see on either end. So there it is, 0.1646. And then it's just about plotting those values. Okay, so 0.13, so we've got each of these data, each of these ticks on the y-axis scale is 0.02. So 0.13, that would be 0.12, so 0.13 is going to be here. Sorry, that's 0, so it's here. Might use a colour other than black so you can see it. When x equals 1, the probability is 0.33, let's say, to two decimal places. So 0.33 is going to be here. Same for when x equals 2. When x equals 3, the probability is 0.16, let's say. So that's 0.1, 0.12, 0.14, 0.16 is going to be here. 0.04, so that's here. And then 0.0041 is really, really small. Okay. So like we saw in the example above, if you just rule in, if you've got a ruler or use the edge of your CAS lid to get a nice straight line, just rule in some vertical lines so we can clearly see. We've obviously got positive skew happening here, and that's because our probability is less than 0.5. Okay, the work today is again from exercises 14A and 14B, but these are the questions where you're going to make use of your CAS binompdf and binomcdf in the CAS to answer the questions.